Alright guys, lesson 9. We're going to prove theorems about parallelograms. This is going to be a long one, but hey, I took a shortcut. So, we know what parallelograms are, but let's go over quadratics. Not quadratics, quadrilaterals. We already talked about quadratics. Now we're going to talk about quadrilaterals. Blech. So, any four-sided polygon is a quadrilateral. This one, check. This one, check. This one, 1, 2, 3, 4, yep. 1, 2, 3, 4, yep. This one's got 4. Ooh, this one's goofy. 1, 2, 3, 4, yep. 1, 2, 3, 4, yep. 1, 2, 3, 4, yep. Those are all quadrilaterals. Trapezoids, as you recall, are quadrilaterals with exactly one pair of parallel sides. Arrowheads are used like tick marks to show that the two lines, segments, or rays are parallel. A lot of you ask me about these things. That just shows parallel. Okay? Parallelograms is a quadrilateral with two pairs of parallel sides. Hence, this line is parallel to that line, and this line is parallel to that one. Could say opposite sides are parallel to each other. Rhombus is a quadrilateral with 4 congruent sides, hence 4 tick marks. Sometimes you see this and it looks like a square, but when we talk about rhombus, we just need to associate the fact that all 4 sides are congruent. Rectangle is a quadrilateral with 4 right angles. Here's one, there's another. One more to go. 4 right angles. Okay. A square is a quadrilateral with 4 congruent sides and 4 right angles. 1, 2, 3, 4. 1, 2, 3, 4. By its definition, a square is a rectangle and a rhombus. It's a rectangle because of the 4 right angles. It's a rhombus because of the 4 congruent parts. Now, is every rectangle a square? No. Is every rhombus a square? No. A square, remember, incorporates both rectangle and rhombus definitions. This Venn diagram kind of helps with that. As you can see, parallelograms take up the most. Rectangles follow parallelogram properties. Rhombuses follow parallelogram properties. And a square is nicely nested in between all of it, and it shares both parallelograms, rectangles, and rhombus identities. Okay? Let's see. So, in the diagram below, ML is a transversal. I know I have a bunch of lines here, but we're looking at ML. This diagonal line is a transversal to 2 different pairs of parallel lines, as you can see with the red triangles. Name the parallel lines and list the alternate interior angles of each pair. Boop. PL is parallel to MG, PM is parallel to LG, and PLM is congruent to LMG, and angle PML is congruent to MLG. Okay. Now I just pretty much cut all that extra stuff off, and as you can see, we see a parallelogram. Okay? So let's start our theorems. So we're going to be given a PLGM is a parallelogram with a diagonal LM. We're going to try to prove that triangle LGM, that's this guy down here, is congruent to this guy up here, MPL. So I added some tick marks to help guide you as far as what we're looking for. And I also typed out these statements and reasons, that way you don't have to look at my nasty handwriting. So if you would like, you could pause and try it on your own. Or B, I'm going to slowly start bringing this little shade down so you can see each step by step. Now, your steps might not be quite exactly like mine, but I just want to remind you that as long as you're justifying yourself correctly, it'll work. So, as always, the first one's given. I literally just copied what was given. Second, since we know what alternate interior angles are, I'm going to say PLM is congruent to LMG. I'm also going to say that angle PML is congruent to MLG, and again, because of alternate interior angles. I know you're keeping your eye on that center there, and you are right. ML or LM is congruent to LM because of the reflexive property. As you can see, I think we have angle, side angle is going to be a postulate we're going to use. And indeed, you're right. Now you're asking, Mr. C, what's the point of this? And I'll tell you, since we just proven that if we draw a diagonal across a parallelogram, we make two congruent triangles. Hence, the theorem. The diagonal of a parallelogram divides the parallelogram into two congruent triangles. Imagine that. Boop. Let's take this parallelogram, ABCD, with diagonals BD. We're going to prove that line segment AB is congruent to CD, and AD is congruent to CB. Or another way to say that, opposite sides of parallelogram are congruent. Let's check. So, as always, we start with what's given. Then, I would just go ahead and argue that two triangles are created when you use a diagonal. Hence, we just proved that on the last slide. So, guess what? Since it's a theorem, you can use it in the reasons. Am I being lazy? Of course I am. And the fact that now that we have two congruent triangles, we can use CPCTC to distinguish that AB is congruent to CD and AD is congruent to CB. Imagine that. Boop. So our new theorem now is opposite sides of parallelograms are congruent. No, this is not the last one. Boop. Parallelogram ABCD with diagonals BD and AC. Now we have two diagonals. We are going to prove that BAD is congruent to DCB, and remember, BAD is right here. BAD and DCB, boom, boom, and ABC, skadoosh, and CDA. Those are the bigger angles. In other words, we're going to prove that opposite angles are congruent in a parallelogram. My button seems to not be working. There we go. So, scroll down. As always, parallelogram ABCD with diagonals BD is given. BD. Seem to have forgotten one. As always, we have triangle BAD. It's congruent to DCB. So keep in mind, I'm focusing on this triangle and this triangle. They're created because of that diagonal. And ABC, this guy, and this guy. You know what? I need to put that in here. And AC. Jeez. So, diagonals created. We got two triangles. This guy, and then this guy and that guy. Again, these letters help distinguish which triangle we're looking at. And as we scroll down, again, I'm taking the lazy path. Angle BAD is congruent to DCB, and angle ABC is congruent to CDA because of CPCTC. In hindsight, we pretty much proven that opposite angles of parallelograms are congruent. Yes, be keeping these in mind because this is going to help you solve the worksheet and future problems down the road. Skadoosh. Parallelogram ABCD with diagonals BD and AC intersect at point O. Boop. prove that AO is congruent to OC and DO is congruent to OB. In other words, do the diagonals bisect each other? So, yes, that is a lot to take in, but I tried to explain myself thoroughly. So, always start off with what's given. You have diagonals BD and AC, and they do intersect at O. Again, this is always given, and it's always first. So, if we have side AD is congruent to BC and side AB is congruent to DC, okay, that's opposite sides are congruent in parallelograms. We proved this a couple slides ago, so that's okay. We can take the shortcut. And the fact that angles ABD is congruent to BDC and BAC and ACD and ADB and DBC and DAC and ACB are congruent to each other. We're going to argue that their alternate interior angles are congruent. That is a mouthful, excuse me. So I try to make sure my marks are all distinguished. Okay, I think you can see where we're getting with this. Oops, trying to scroll down there. We're going to state that triangle AOB is congruent to COD and AOD is congruent to COB using angle, side, angle. Angle, side, angle. So we have all these four congruent triangles toward opposite sides. And what I mean by that, I'm saying this triangle over here is going to be congruent to this triangle. And I'll put this as a square. This triangle is going to be congruent to this triangle. And as you know, I think you see it coming, CPCTC is going to state that AO is congruent to OC and DO is congruent to OB. I know that was a lot to take in, but this was just the proof to show that diagonals of parallelograms bisect each other. Skadoosh. Okay? Boop. Trust me, we're almost there. Rectangle ABCD with diagonals AC and BD, let's prove that AC is congruent to BD. Essentially, we're proving that in rectangles, the diagonals are congruent. So, starting off, again, what's given? AD is congruent to BC because opposite sides of parallelograms are congruent. DC is congruent to DC because of the reflexive property. So if you look, if you can see my cursor, we're looking at this big triangle here and this big triangle over here. So now we have triangle ADC is congruent to BCD because of side, angle, side. Let me write it, side, angle, side, and side, angle, side, if you can see it. And we're just going to wrap it up with a simple CPCTC showing that AC is congruent to BD. Hence, in rectangles, the diagonals are congruent. Alright, give this proof a shot. Here's the answers. Alright, so again, start off with given. We have our reflexive property. DAC is congruent to BAC because of side, side, side. And angle DAC is congruent to BAC because of CPCTC, meaning that the square with the diagonal, these angles will be bisected. Okay? Let's see, is this Let's see if I'm on the right track here. Pikachu again. Yeah, this should be your paper. But again, I'll provide the answer key for you, so all you have to do is reference it. These are pretty easy, because again, opposite sides are congruent now. Let me just get my marker. 135. Not corresponding. Consecutive is the word I was looking for. Consecutive angles add up to 180. Consecutive angles again add up to 180. Opposite, 98. Opposite sides are congruent. Let's see, if it says RT is 19.8, that's right here. Notice I'm drawing on my diagram to get things planned out. It says find RP. Well, that's bisecting each other, so that means this should be 19.8. So just add those two up, or double it. 8 here, let's see, we got 60 here, 52 here. As I stated before, consecutive interior angles add up to 180. So maybe one way to solve this is to go 180 minus 60, which gives us, what do we get, 120? You spent 52, so let's subtract 52. And, well, it's late. I can't think right now. 120 minus 52, we get 68. Boom. Degrees. Let's look. KM. Let's see. K. Huh. Well, don't know where M's at. Don't even know where these letters at. Let me go back to my other slide. Aha. So again, KM, the whole thing is 23.4. All you got to do is divide by 2 to get half that, which is the YM. Let's see here. Again, I'll let you do this, but just remember, consecutive add up to 180. So you're going to go 180 minus 55. Take that answer, subtract 62 from that, and you'll get your answer. Again, consecutive interior angles will add up to 180, so I'm simply going to go 80 plus 11x minus 10 should equal 180. Opposite sides equal, so 2x plus 15 equals x plus 15. I'm not finishing these. You can finish it. I'm just starting you off. Again, consecutive, 9x plus 15, add 6x plus 15. All that should add up to 180. Same thing here, 35 plus 14x plus 5 should equal 180. Opposite, 7 should equal x plus 1, 1. And again, consecutive interior, 130x plus 50x should add up to 180. And again, you can just check the answer key for the rest of these. Alright, good night. Oh, let's say bye to Pikachu first. Where did he go? Good night, Pikachu.